Hi there! I'll introduce you to the Spark machine learning library made by researchers at UC Berkeley. The ML library has been developed since late 2014 and is going to replace the current machine learning library MLlib. This is of course very interesting if you want to be on the frontier of big data advancements. So, why is Spark ML so useful? And why is it so frequently used for big data analysis? Let's see. Spark gives you the possibilities of partitioning your processing of big data sets onto a cluster of worker machines. The multi-stage in-memory processing also makes Apache MapReduce jobs about 100 times faster than Apache Hadoop, a similar package. The RDD data structures makes the data processing easy parallelizable. Spark is implemented in Scala, Java, Python, and R, but we'll only go through a Python example. As you see in this plot comparing logistic regression using different platforms, Spark MLlib has a strong scalability with the number of machines. So Apache Spark is fast for some purposes, but does it also have all we need included? Of course it does. The goal of Spark is to make a general purpose platform where the user can process the data without stepping out, as the cost of switching platform is high. Therefore Spark ships as a full package with Spark SQL for data structure, Spark Streaming for streaming data, MLlib for machine learning, and GraphX for graph representations. These libraries can work and build on top of the fast data handling of Spark. We'll focus on the machine learning part and also use Spark SQL. MLlib uses the data structures of the Spark core. So what kind of models can we hope to be able to build with MLlib? Let's have a look. MLlib does of course most of the methods known for machine learning. These include linear models, Gaussian mixture models, and principal component analysis, among others. We only show the main areas of machine learning algorithms present in Apache MLlib, but go have a look at the MLlib documentation to explore all the possible algorithms. However, Apache Spark is in such rapid development that it was decided in 2014 to redesign MLlib into a new, higher level and more flexible library called ML, which is our focus. So, what are the changes and what has improved? The main motivation for changing into ML is to have optimized workflows. The processing structure and standardization of classes and methods is inspired by Python's scikit-learn, where all models can be trained and predict using the same setup. This, of course, needs a general data structure with all the information needed to be passed on through the methods. MLlib uses RDDs, which are resilient distributed dataset, and Spark's fundamental programming abstraction. These cannot describe structured data, so Spark SQL's data frames, also known from R and Python module pandas, are used instead for ML. Of course, not all functionalities are presently available, but we will still go through the use of Spark ML, as it is the future of machine learning with Spark cluster computing. Currently, Spark ML implements feature extraction, transformation, and selection, decision trees for classification and regression, examples like random forest and gradient boosted trees, linear methods, logistic and linear regression, of course, and multi-layer perceptron classifiers. Okay, let's look at the fundamentals of Spark ML. To understand the workflow in Spark ML, we need to know the key concepts included in the interface. These are data frames, transformers, estimators, and parameters, which are identical for transformers and estimators, and lastly, pipelines. Now we'll take a closer look at these concepts. The data frame is tables in a relational database, where all columns are named and therefore are perfect for general use through all methods in the pipeline. You probably know data frames from R or pandas in Python. Data frames can be created from many sources like files or regular RDDs, and can handle a variety of data types. Each column in a data frame is named, for example, features and labels in a machine learning context. A data frame is usually raw data. To change this data into something which can be used in a model, these are pre-processed using transformers. Transformers are algorithms which transforms one data frame into another using the method transform. They are divided into two types. Firstly, feature transformers, which extracts, modifies, and selects data, for example, tokenization of text into words, feature hashing, and normalization of feature vectors. Secondly, there are learned models, which is the result of estimators and transforms a data frame into a new one called predictions. An estimator is a learning algorithm which are fitted or trained on a data frame. The result is a learning model, which is in itself a transformer. Both estimators and transformers use the same parameter framework. The power lies in pipelines in ML. Transformers and estimators can be chained together in a sequence of stages, which a data frame can be passed through. However, since an estimator returns a model and not a transformer, estimators are fitted on a data frame beforehand to turn them into transformers. A pipeline itself is an estimator and is fitted on a data frame, turning it into a pipeline model. Now, having introduced Spark ML, we will use this in a data classification example. Our data is a Reuters news data feed containing more than 21,000 articles. The classifier to be created has to be able to determine if the article has the topic earn from the article body text. This is a supervised learning problem with binary classification, for which we will use logistic regression in Spark ML. Before we are able to use Spark ML, we have to convert the data from a JSON file to a data frame and run some initial pre-processing steps. The articles are read line by line using Python JSON module. Articles without topics or body are discarded. Label values are created as a binary class vector determining earn in topic, and afterwards the data is converted to a data frame. Lastly, the data frame are split into test and training sets. So now we are ready to use Spark ML to perform the estimation. We define a pipeline estimator containing 3 elements, which is the tokenizer transformer, which is transforming the article bodies to a list of words. Afterwards, we have the feature hashing transformer, which is hashing the words into feature vectors. And lastly, we have the logistic regression classifier training a model on the feature vectors with earn booleans label untouched by the transformations. And this is how the code looks in Python. Notice how the transformations first are defined and combined as a general pipeline estimator in the 4 first lines, and only applied to the data by running the method fit of the pipeline estimator on the training set, creating the model in the end. Predictions are easily made by transforming a test set using the resulting model. This model is itself a transformer that takes the test data frame and returns predictions of the topic earn by tokenizing, feature hashing, and applying the logistic regression model with the method transform. In Python, the code looks like this. Test predictions are returned from the model transform method applied on the test set. To evaluate the performance of the model, we use a binary classification evaluator and use its method evaluate on the test predictions. Now, let's look at the running code. Now, I want to show you our script for the logistic regression classification. First of all, we have to make our setup where we set up our Spark contexts, we set up our SQL context. Afterwards, we do the pre-processing of the articles in the JSON format, and we convert them into a data frame with the labels text and label. These we split into a training set and a test set. Then we want to make our pipeline estimator. We put it together with a tokenizer, a feature hasher, and the logistic regression using max iter equal to 10 and regularization parameter equal to 0.01. And we put these together in a chain in the pipeline. Then we want to train our model using the fit method in the pipeline on the training set. Afterwards, we can use the model for making predictions from the training set and from the test set. Then we want to evaluate these predictions using a binary classification evaluator. And we get the training accuracy and the test accuracy. So now I would like to run the shell script, which sets up a Spark environment and runs the Reuters LR Python script. And now it's done. And as you see, after evaluating the training set and the test set, we achieve accuracies of 100% for the training set and 97.5% for the test set. which is quite high accuracies, but understandable since a human eye would have no problem in distinguishing between a news article and a list of stock prices. So the entire program took 27 seconds, but the CPU runtime was 48 seconds. So the parallelization using the two cores of the computer nearly halved the runtime compared to using a single processor. But can we do better? We can do better, of course, by using cross-validation. Earlier, we used default values for the parameters of the logistic regression. Now let's tune these hyperparameters using the cross-validator class. The cross-validator class gets 4 inputs: an estimator, which is our pipeline, the parameter grid, which is the grid of values for the parameters which we want to tune, and an evaluator, which is the objective function and is the binary classification evaluator. And last of all, numfold, which is the number of data partitions in a cross-validation. We use 3. So let's look at the new code. Now I'll show you how we put a cross-validation on top of our fitting of our model. We, of course, use the same part as before, the same pre-processing, the same pipeline estimator and everything. But then we want to make our cross-validator. And the cross-validator needs a parameter grid. The parameter grid is made of regularization parameters, which are these 3 different, and it's made of maximum number of iterations in the logistic regression, which are these 3. And therefore, we get a 3x3 grid. And the 3x3 grid we can use in our cross-validator. And our cross-validator takes the pipeline in, and the grid in, and the evaluator in. And then we use 3 for the number of folds in our cross-validator. So the cross-validator will make 3 partitions of the data set 3 times with 1/3 of this validation set. And then we fit our model on the training set like before, but now 27 times, so we can expect a much higher runtime. And then we get the predictions again, hopefully enhanced. And I'll run the shell script again, which is setting up the Spark environment and running the Python code. Now it's finished with a bit higher runtime. We see that the test set accuracy is 97.9 for our cross-validated model. And the total runtime was 3 minutes and 38 seconds. But if we would have utilized more cores, this would have been dramatically reduced because SparkML can parallelize the cross-validation. To conclude all this, we'll sum up the advantages and disadvantages. On the plus side, SparkML is a general-purpose big data package that scales very well using parallelization. It uses a standardized set of classes, which makes it highly flexible. Other than that, Spark is an actively developed framework, and new features and upgrades are added often, so we can expect the ML library to be fully established in the near future. On the other hand, the overhead is large, resulting in poor single processor performance. On top of that, a lot of functionalities are currently missing, and the ML library exhibits teething troubles. Hope you enjoyed the presentation, and we wish you good luck in your further exploration of this framework.